Welcome to this lecture in Geographic Information Systems in Water Resources on spatial analysis. Here are the learning objectives. By the end of this class, you should be able to describe some of the ways continuous surfaces or spatial fields are represented in GIS. You should be able to list the data elements that comprise a grid data structure, describe how integer, categorical, and real value data fields are represented using grids, use map algebra to perform raster calculations on grids, and explain the scale issues involved in raster calculations where grids may not all have the same cell size. You should be able to define interpolation and describe aspects to be considered when interpolating spatial data, use interpolation to determine watershed average properties, precipitation, and that will be the exercise that we do next time, and also calculate the slope of a topographic surface using three different methods, the one from ArcGIS, the one from the D8 model, and the D-infinity model that I've developed. For this class, there's a number of readings that are assigned. The first two are from the ArcMap help that gets into reference information in the What is Raster Data section of the help. This part of the web page, just read this first section, the basic data that tells you what raster information is. Then in fundamentals of raster, I'd like you to read from cell size, raster bands, how features are represented in raster, discrete and continuous data, raster dataset zones, and raster dataset attribute tables. Those should give you the basics that we'll be using here. Also, this link will take you to the ArcGIS Pro help on the Spatial Analyst Toolbox. That describes some of the tools that are available. Read this just to get a general sense of the tools available. And some of the ones that we will use now or later are listed on the tool set. There's also two links on how the slope tool and how the aspect tool works. Those will be two of the key tools that we use in the class. With raster data, we're often thinking of representing a continuous surface, and we want to represent it. There's a number of ways that it can be represented numerically. The grid or raster is what's shown on the top right, where basically you've got a set of numerical values, grid cells, that encode and numerically represent what may be, say, an elevation field. There are also other ways that can be represented. A triangulated irregular network uses randomly or irregularly located points and then fits triangles in between them, interpolates the points between them to effectively represent a surface. And then there's a contour and flow line model that could also represent the surface in terms of contours and flow lines. In this class, we're only going to be working with the raster data. The contour and flow line model was actually published in some hydrology work in Australia, but doesn't have an ArcGIS implementation. So thinking about the raster representation of geographic information, we have a grid that really defines geographic space as a mesh of identically sized grid cells. Each cell holds a numeric value that measures a geographic attribute like elevation for that space. When we think of representing geographic information, there's really two ways, raster and vector. And both are different ways to encode and generalize geographic phenomena. Both can be used to represent fields and discrete objects. But in practice, there's a strong association between raster and fields and vectors and discrete objects. So what we're thinking about here is really the sort of spatially continuous information or fields that are widely used in hydrology. One of the most common forms of of a grid is a floating point or real valued grid, which might represent a continuous surface using floating point or decimal numbers to represent each grid cell. It's also possible to represent a polygon as a zone of cells, and that would be the approach used for discrete objects. Polygons, recognizing polygons are discrete objects. So the grid data structure. A grid is defined by its extent, the number of rows and number of columns, the spacing or the cell size of those individual columns, the top left and bottom and right coordinates, positioning where that is in space, as well as how no data values are encoded. And again, the values that are included in a grid can be real numbers or integer. In the case that they're integer, they can also have a table referred to as a value attribute table associated with them. So for example, that's helpful to provide additional metadata about the gridded values. So the grid may just hold integers that may initially not be readily interpretable, but when associated with the value attribute table, you can see things like the type of land or the area or some other encoding that might be associated with those attributes. When working with raster data, it's also important to think, what do the values at the grid cells actually mean? And this slide from the National Center for Geographic Information Analysis core curriculum on GIS science points out that a grid value may represent the average over the spatial footprint or the spatial scale of a grid cell. It may represent values sampled at the centers, or sometimes it may represent values sampled at grid nodes. With ArcGIS, we're almost always using either 1 or 2, because 3 can be interpreted as just a 2 with a half grid cell shift. But the interpretation of how these, how the data was actually encoded or obtained is important in terms of using the data. There's also a dependency on size, and this illustration taken from one of the ArcGIS help files makes that point. If you have fairly large cell sizes, as we have on the right, you get a fairly coarse representation of what might be this polygonal shape, perhaps Gulf sand trap. Then as moving a little bit to the left, you get smaller cells and smaller cells. You actually have to have higher resolution data, but you get higher feature spatial accuracy. You get slower display and slower processing and larger cell sizes. So there's a trade-off between how accurate the information is represented and the scale or cell size. There's also a question of how that information from the precise edges of a feature or the polygons are converted into grids. What is the rule that's used? And what's shown here are two possible rules. One is the largest share rule, where perhaps you've got grid cells and you find the largest value of whatever the quantity is, and you encode that in the grid value. Or if you use the center point rule, maybe if there's the hole and the center point falls in the hole that represents the smaller area, you would get a different approximation. So these are some of the things that you have to consider when using a grid to represent spatial information. So to summarize some of the key concepts, in working with grid or raster data structures, they represent surfaces as an array of grid cell sizes, and generalization is an inherent part of the representation, and how things are generalized is important to know in terms of being able to interpret and work with gridded data. I'm going to pause in this lecture now and continue with map algebra and raster calculations a little bit later.